Start. Good morning, everyone. Respected HOD Professor, Department of Mathematics, PG Department of Mathematics, Professor S.P. Rai sir. My external Professor A.K. Thakur sir, which is the head of Department of Guru Ghasidas Vishwavidyalaya. My supervisor, Dr. Dinesh Kumar Maji sir, Dr. Ravi sir, and all HOD of different college department and all research scholars. So first, the topic of my thesis is mathematical modeling of elastic wave in different layered media. These are outlooks. First is abstract. Chapter 1 is introduction. Chapter 2 to 5 is my thesis problem. And chapter 6 is summary and conclusion. And last references. These are abstract. In chapter 1, introduction and review of literature. General introduction on seismology and earthquake. Seismology is a branch of applied geophysics that focuses on the study of earthquake and the propagation of seismic waves. The branch of geophysics investigates both the mechanism of earthquake and the field of internal structure. Experts study seismic wave behavior and earthquake phenomena are referred to seismologists. The term of seismology originates from two Greek words, seismos meaning earthquake and logos meaning study. Earth structure. It is well known that the Earth structure is mainly divided into three parts: crust, mantle, and core. Classification of seismic wave. Seismic wave are the wave of energy caused by sudden breaking of rocks within the Earth or exploration. The seismic wave of various types of propagation from the source in all directions through the Earth's entire and recorded at the large distance by a sensitive instrument placed on the near of the Earth structure. There are two types of seismic wave. First is body wave and second is surface wave. Body wave is also two types. First is P wave and yes sir. Body wave is two types. कुछ बोल रहे हैं सर?
No, continue.
Body wave is two types, P waves and S wave, and S wave is also two types. First is SH wave and SB wave. Generally, surface wave is three types. First is Love wave, second is Rayleigh wave, third is torsional waves. The animation part of P waves. This is the animation part of P waves. Particle motion consists of alternating compression and dilation. Particle motion is parallel to the direction of propagation. Material returns to its original shape after wave passes. Shear wave. This is also called S wave. The animation of the shear wave. Particle motion consists of alternative transverse motion. Particle motion is perpendicular to the direction of propagation. Transverse particle motion shows here in vertical but can be any direction. However, the earth layer tends to couch mostly vertical. And horizontal shear wave. Material returns to its original shape after wave passes. Particle motion consists of alternating transverse motion. Particle motion is horizontal and perpendicular to the direction of propagation. This is the animation of Love wave. And Rayleigh wave. The animation of Rayleigh wave. A particle motion consists of elliptical motion in a vertical plane and parallel to the direction of propagation. Amplitude decreases with depth. Material returns to its original shape after wave passes. We also discussed the body wave and P wave and S wave, surface wave. We also discussed the Love wave, Rayleigh wave and torsional surface. In torsional surface wave, beside the Rayleigh and Love wave, the third type of surface wave known as torsional surface wave can exist in non-homogeneous Earth. Torsional wave involve a periodic rotational and or twisting motion of particle along the propagation direction. The amplitude of torsional wave exhibits exponential decay with increased depth. Dispersion relation. This is the classical equation of Love wave propagation. Basic theory of elasticity. This is the historical development and review of literature. In chapter 2, the topic of chapter 2 is effect of non-homogeneity and initial stress on torsional surface wave propagation in initially stressed pro-elastic medium bounded by a heterogeneous layer and half space. This is the introduction of this topic. This paper is published in Mechanics of Solid. This is introduction part of my paper. The geometric problem of this paper. In this problem, we discuss torsional wave propagation in initial stressed porous layer having thickness H1, sandwiched between upper heterogeneous layer having finite width H2 of linear variation in rigidity and density, and a lower half space having infinite width with exponential variation in rigidity and density, respectively. Here we have considered an isotropic of porous layer, which is also water situated under initial stress P. Solution of the problem. The solution of upper layer M1. The equation of motion for this layer is equation of 2.1, where sigma r theta and sigma r zeta z theta are the components of stress. V denote the components of displacement, and rho1 is material density. The rigidity and density of upper layer are assumed in linear function of distribution. Mu naught equal to mu naught 1 plus Az, rho1 equal to rho naught 1 plus Bz, where mu naught, rho naught are the value of mu1 and rho1 at z equal to 0 respectively, and AB are the constant having dimension that have inverse of length. Using a strain relation, we find the equation 2.3. By equation 2.2, equation 2.1 change to equation 2.4. They are taking the non-dimensional coordinate as r equal to a small r by capital R and zeta equal to zeta naught plus z by L, where zeta naught being a constant and 1 by L being a wave number, where k equal to 1 by L, then equation 2.4 reduced to 2.5. Using the variation of partial differential equation, variation of separable and variable, we can find the equation 2.11. Solution of layer M2. The dynamic equation of motion of pro-elastic type media under the influence of comprehensive initial stress is obtained by Barth and Wyckoff for equation 2.1 to 2.17, where A, F, G are denote the elastic constant, G and N also denote the model of the anisotropic layer in Z direction and radical direction respectively. And solving this, we find the equation 2.34. Solution of half space M3. Governing equation of motion relating to torsional type surface wave reduced as equation 2.35, where V3 is displacement and theta is direction. The relation between respective stress and displacement component is equation 2.36. And using the equation 2.36 and equation 2.35, we find to equation 2.37. And solving this separable and variable, we find the equation 2.44. Boundary condition and dispersion equation. For this model, we have boundary condition as follows. First, there are three conditions. First is displacement and stresses should be continuous at common interface of M2 and M3, that is Z equal to 0. There are two parts, A and B, and displacement and stresses should be continuous at a common interface of layer of M1 and M2 at Z equal to minus H1. There is two types A and B, and third type of case, the upper part of M1 is free from trace, that is Z equal to minus H1 plus H2, that is del V by del Z equal to 0. And using the boundary condition of equation first, second, third, we find the five equation 2.45 to 2.46 to 2.47 to 2.48 to 2.49, and solving and eliminating the constant of A, B, D, and D1 and D2. So from equation 2.45, equation 2.46, equation 2.47, equation 2.48, and 2.49, we find the equation 2.50. This is the represent the dispersion equation of torsional surface wave. Validation and problem. This is the equation of 2.5, is validation of validation of the problem. Numerical computational of part. And this in figure 2.2, this shows that in figure 2.2 shows that the effect of AL of phase velocity. This figure shows that the phase velocity increase with increasing value, rigidity, heterogeneity parameter associated with the upper layer. In figure 2.3, shows effect of BL on the phase velocity. This figure shows in figure 2.3 shows effect of BL on the phase velocity. This figure shows that the phase velocity remain constant with increasing value of density heterogeneity parameter associated with the upper layer throughout. In figure 2.24 shows the effect of ML on the phase velocity. It shows the phase velocity increase with increasing value of heterogeneity parameter associated with the lower half space. The prominent impact of ML can be seen on the phase velocity and with the increment of heterogeneity after 1.0. Very less impact on the phase velocity can be seen. And equation figure 2.5. The figure shows that effect of NL on the phase velocity. The phase velocity shows very less impact of NL on the initial wave number, but as the wave number increases, the phase velocity curve being constant and attain a stable stage. In figure 2.6 shows effect of initial stage parameter zeta on the phase velocity. This graph shows that the phase velocity monotonically increases with descending values of initial stage parameter of torsional waves. This is conclusion. We can also discuss in chapter 3. The topic of chapter 3 is propagation of torsional wave in an isotropic layer sandwiched between a heterogeneous layer and half spaces. This is a communicated paper. This is the introduction part of my paper. This is the geometry part of my paper. We consider in this geometry we consider that torsional surface wave for a system consisting of a heterogeneous layer M1 with exponential variation in rigidity, density, and initially a stress, an isotropic layer of sandwich ascension M2 with hyperbolic variation in elastic model density and initial stress, and covering a heterogeneous dry half space M3. Solution of the problem. Solution of the upper layer M1. The governing equation of motion relating to torsional surface wave is equation 3.1, where V1 is displacement and theta is direction. The relation between a stress and displacement components is given by equation 3.2. And using the equation 3.2 and equation 3.1, we can reduce the equation 3.3. Using the variable of separable, we find the equation and solve it. Using the first kind of Bessel function, we find the equation and solve this equation 3.10. Solution of layer M2. If r and theta are radial and circumferential coordinate respectively, the equation of motion, the initially stressed and isotropic layer is given words of equation 3.11, where V2 is displacement along the theta direction, P is initial comprehension stress in the medium, and rho2 is density of the medium. S z theta is incremental stress components and isotropic elastic layer, and they are given relative. Using equation of 3.1, we can reduce the equation 3.12. Using the variable and subvariable, we find the equation 3.18, solution of half space M3. The dynamical equation of motion are equation 3.19, where this usual symbol is usual, meaning the stress relation is we find the equation 3.21, and solving this we find the equation 3.32. Boundary condition and dispersion equation. There are three types of boundary condition. Displacement and stress should be continuous at the common interface of M2 and M3, that is Z equal to 0. There are two conditions, A and B is given. And second case, displacement and stresses should be continuous at the common interference of layer M1 and M2, that is Z equal to minus H1. There are two cases, A and B is given. And case third, the upper part of M1 is free from the trace, that is Z equal to minus H1 plus H2, del V1 del Y Z equal to 0. By boundary condition, we find this. We find the equation 3.38. Particular cases. In case 1, if L H1 tends to 0, M H1 tends to 0, then the dispersion equation 3.38 reduced to equation 3.39. In case 2, if alpha H1 tends to 0 and N naught equal to L naught, then the dispersion equation 3.38 is reduced into equation 3.40. In case 3, if AH1 tends to 0, then this dispersion equation 3.38 can be reduced as 3.41. In case 4, if alpha H1 tends to 0, AH1 tends to 0, and N naught equal to L naught, then the dispersion equation is 3.38 reduced to equation 3.42. And case 5, if LH1 tends to 0, MH1 tends to 0, AH1 tends to 0, then the dispersion equation 3.38 reduced into equation 3.34. And solving this, we can find this equation 3.49. This is numerical and computation and discussion. And figure, we now solving this figure in figure 3.2. In this figure, 3.2 shows dimensionless phase velocity against the dimensionless wave number for different value of LH1. It shows that as the heterogeneity parameter of rigidity increase, the phase velocity increase. In figure 3.3, in this figure 3.3 shows dimensionless phase velocity against the dimensionless wave number, different value of MH1. If tells that the phase velocity decrease with and increases the heterogeneity parameter of density. In figure 3.4, figure 3.4 shows that the dimensionless phase velocity against the dimensionless wave number for different value of alpha H1 in the sandwiched layer, the phase velocity increase as the heterogeneity parameter increase. In figure 3.5 shows that dimensionless phase velocity against the dimensionless wave number for different value of initial stress parameter zeta in the sandwich layer. As the initial stresses increase, the phase velocity decreases, indicating the reduction in wave propagation speed. In figure 3.6, in this figure 3.6 shows that the dimensionless phase velocity against the dimensionless wave number for different value of AH1, the heterogeneity parameter positively influence phase velocity with higher value, leading to increased phase velocity. In figure 3.7 shows dimensionless phase velocity against the dimensionless wave number for the different value of n. As the value of n increase, the phase velocity of torsional surface wave increase. This is conclusion. We can also discuss in chapter 4. In chapter 4, this is my problem. The topic of my problem is propagation of love type wave in an isotropic media sandwiched between two initially stressed orthotopic media. This paper is published in Journal of Vibration Engineering and Technology. This is the introduction of part. This is the geometry of problem of this paper. In this paper, in this problem, we can discuss the present model has been taken with two initially stressed orthotopic half space and a homogeneous isotropic media. Half space in homogeneous isotropic media of finite thickness H. Let mu1, mu2, mu3 and ρ1, ρ2, ρ3 be rigidity and density of medium M1, M2 and M3 respectively. Solution of the problem. Solution of upper half space. Dynamical equation of upper half space with initial stress rho P1 obtained along x-axis from equation 4.1. Using the stress and strain equation, we find the equation 4.3, where Bij, V symbol is same. Using, we find the equation 4.47. Solution of middle layer, the dynamical equation of motion of middle layer of love 9011. The equation of is 4.8, where U2, V2, and W are components of this displacement along x, y, z axis, and sigma ij incremental stress components, and ρ1 is density. In homogeneous medium, using Hooke's law from equation 4.9, where lambda mu1 are lemma constant. From equation find V4, equation 4.10. The love type wave characterized, we find the equation 4.10, and solving the variable of separable, we find the equation 4.14. Solution of lower half space. Dynamical equation of motion of lower half space with initial stress P3 operating along x-axis in love 90. In equation, we find the equation 4.15, and solving this equation of variable and separable, we find the equation 4.21, which is the boundary condition and dispersal equation. They are the boundary condition. The weight of middle layer M2 in H at Z equal to minus H displacement components are uniform. So boundary condition at Z equal to minus H. There are two parts, 1 and 2nd. By solving, eliminating arbitrary constants C1, C2, C4, C6 from equation 4.22, 4.23, and 4.24 and 4.25, we get and we find the equation 4.26. This is the dispersal equation of wave. Particular cases, in case 1, when both upper and lower are without initial stresses, P1 tends to 0, P3 tends to 0, then the equation 4.2 reduced to equation 4.27. Equation 4.27 represents love wave dispersion relation in homogeneous medium situated between two stress-free orthotopic medium. In case 2, when we remove the upper half space, we get equation 4.28, and equation 4.28 represents love wave dispersion relation in homogeneous medium placed above the stress-free orthotopic medium. In case 3, when we convert lower orthotopic media to homogeneous medium, we find the equation 4.29. This is the classical love wave. The validation solution of love wave is homogeneous medium sandwiched between two initial stress orthotopic medium. This is numerical and computational, numerical, computational, and discussion parts. In figure 4.2 shows, normalized phase velocity versus normalized wave number for various ratio of B1 by B2. It has been found that as the ratio of B1 by B2 increased from 1.5 to 2.0, then velocity decreased significantly. Also, the phase velocity decreased throughout as the wave number increased. In figure 4.3, shows normalized phase velocity against normalized wave number for various ratio of Q33 by Q31. It shows that there is a very minute change in the magnitude of the velocity as the ratio of q33 by q331 is slightly alternating its increase as the value of the ratio increase. Also, the curve are concluding at the point where although the ratio change but the magnitude of velocity remains constant. In figure 4.4 shows that normalized phase velocity against normalized wave number for various ratio of q1 by 3 by q11 by, where the value of ratio q1 by 1 by 1 3 by q11 increase, the magnitude of the velocity increase. In figure 4.5 shows the normalized velocity against normalized wave number for various of q3. In figure 4.6 shows normalized phase velocity. This is the conclusion part of my in chapter 5. In chapter 5, the topic of chapter 5 is effect of initial stress and inhomogeneity on the love. So Umar ji आवाज आ रही है, आपको आवाज आ रही है. Effect. The topic of chapter 5, effect of initial stress and inhomogeneity on the love wave propagation in an inhomogeneous composite structure. This is the introduction part of my problem. This is the geometry of the problem. The model presents a homogeneous media bounded by two inhomogeneous half space with property varying linearly in rigidity and density. In the x-axis direction, the weight of the bounded layer H is considered along the direction of wave propagation. The origin is situated at intersection of homogeneous media and lower semi-infinite half space M3. Half space M1 and M3 are under the influence of initial stress ρ1 and ρ3 respectively. Solution of the problem. This is the solution of the problem. Solution of intermediate layer in solving this boundary condition and dispersion equation. At the intersection of M1 and M3, the displacement components are uniform at z equal to 0, where yz equal to zy. In case 2, the weight of middle layer in H, the displacement components at z equal to h is uniform, so boundary condition z equal to minus h it is here. And this solving this, we solve and eliminating the arbitrary constants C2, D2, D1, D3 from the equation. We find the equation 4.5.43. Particular cases, case 1, if initially all the three medium are stress, if P1 equal to P2 equal to P3 equal to 0, we solve the equation. Solving this, and case 2, if the three medium are stress free, P1, P2, P3 equal to 0, A1 equal to P1, and A1 tends to 0, A3 tends to A1, A3 equal to B3, A3 tends to 0. Therefore, the required equation is given. In case 3, if all three medium are stress free, if that is P1, P2, P3 equal to 0, and A1 equal to B2, and A1 tends to 0, A3 equal to B3, and A3 tends to 0, then the upper half space absent, the required equation is given this. This is classical form of love type wave. This explains the authentic of the current problem of the validation. This is the numerical part of this paper, and this is the graph of my problem. In this graph 5.2 shows effect of rigidity heterogeneity parameter attached to upper half space. The phase velocity is observed to increase with increasing value of rigidity heterogeneity parameter. In figure 5.3 shows that the density heterogeneity parameter attached to the upper half space. It has been found that the phase velocity decrease as the value of this density heterogeneity parameter increase. In figure 5.4 shows that effect of rigidity heterogeneity parameter attached to the lower half space. The graph tells that the phase velocity rise as the rigidity heterogeneity parameter increase. In graph 5.5 shows the effect of density heterogeneity parameter attached to lower half space. The graph shows that the phase velocity rise as density heterogeneity parameter increase. In figure 5.6 shows that the initial stress attached to the upper hyperspace, it has been found that the phase velocity increased with the increasing value of initial stage. And figure 5.7 in figure 5.7 shows that effect of initial stress attached to lower hyperspace, it has been found that the phase velocity increase with the increasing value of initial stress. This is the conclusion part we will also discuss. This is summary and conclusion. This is chapter 1, chapter 2, we will also discuss. This is chapter 3, this is chapter 4, this is chapter 5. This is the future scope of the study we can find. These are references.
Okay.
List of application and communicated paper. This is sir. जी sir.
Okay. Manish, nice
Yes, sir.
presentation. Nice presentation. And some question from my side.
Yes sir.
May I audible?
Yes sir. I am audible.
Okay, okay. So the first of all, the presentation is very nice. Some question regarding your thesis. You have used love waves.
जी.
What is the love waves? Who invent and when it is invented?
Love is a seismic wave. This is the surface wave. This is a kind of surface wave. The discovery of love wave is AHE Love in 1911. August Love in 1911 who discovered the love.
Okay. And who invented this?
AEH Love. August.
Yes. And during your thesis work,
Yes,
what
sir.
we observed here, you have used the general form of the second order linear hypergeometric hyperbolic PDE. What is this?
Yes, sir. Yes, sir.
General linear hyperbolic PDE.
Yes, a partial differential equation. Just second order. A u xx plus b v u y plus c xy plus d e xy and g. This is the function a g f g is a function of xy.
Yes. And and one more, you have used the basis function.
Yes, sir. Yes, sir.
I think in chapter 3rd. So what is this?
Bessel's equation is partial differential equation. This is used in this problem. We can discuss this.
What is the formula? What is the mathematical result?
This is, sorry, sir. I can.
What is-
Sorry,
Okay.
sir. I cannot recall this.
In each and every chapter, you have used variable and separable, variable and separable.
Yes, sir. Yes, sir. There
What
are
is
two
it?
types. If variable and separable, we partial differential equation with linear partial differential equation, and there are two types used in linear partial equations, and second type of linear equation we can do. फिर homogeneous equation are used in this.
Okay, can you define when we use the partial differential equation? When we use partial differential equation.
First is linear partial differential equation capital P plus capital Q equal to R. This is the linear partial differential equation we use.
Okay. And you have used in the respective boundary conditions.
Yes, sir.
Can you define what type of boundary equation you have used? And what is the need?
लेयर वाइज बाउंड्री कंडीशन, जैसे जो प्रॉब्लम में M1 M2 M3 जो लेयर है उसका कंडीशन में किसी में स्पेस फ्री रहता है उसमें, फिर केस 1 में जो बॉन्डेड रहता है उसमें उसके अनुसार हम लोग सॉल्व किए.
Okay. आपने each and every chapters you have used and so many figures. What type of mathematical tools you have used here?
This is the tools of MATLAB and something.
Can you define any picture and go to the slide and go to the slide and figure 5.2.
It was a slide man. Slide man.
Go to the 5.2, 5.3, and many more pictures and you have been established by MATLAB.
Yes, sir. Yes, sir. This is the figure of 5.2.
Okay. What the layer means and layer, some colors, there are three types of colors we have used here. What it indicates that?
In layer such that the rigidity heterogeneity parameter attached to upper half space, the phase velocity is observed to increase with increasing value of the rigidity heterogeneity parameter.
And and the second 5.3.
In figure 5.3, shows the effect of density heterogeneity parameter attached to upper half space and has been focused that the phase velocity decrease as the value of density heterogeneity parameter.
Go to the respective and आगे जाइए.
Yes, sir.
Say this more.
In this figure shows that the effect of rigidity heterogeneity parameter attached to the lower half space, the graph tells that the phase velocity rise as rigidity heterogeneity parameter increased.
What is the difference between these three types of figures?
Difference between this is
Why you have used the three types of figures and have some differences ना?
okay.
कुछ ना कुछ तो डिफरेंस होगा ना इसमें. आपने थ्री टाइप्स ऑफ प्लेयर को जो है ना अलग अलग पैरामीटर के अकॉर्डिंगली जो है ना मेंशन किया है. व्हाट इट इंडिकेट्स, क्या इंडिकेट करता है इसको? कंक्लूड कीजिए.
Yes, sir. This figure shows the three different rigidity heterogeneity parameter attached to upper half space. इसमें जो है half space upper density को heterogeneity parameter attached to upper half. Effect of rigidity heterogeneity parameter attached to lower. इसमें एक lower है एक upper है, उसी में differences between.
How many papers you have published?
There are 3 papers in published, sir.
All are in Scopus?
Yes, sir. Yes, sir. There are these the list of publication and communicated paper is here.
Okay. What is your future plan? After getting the degree, what is your future plan?
The future scope of this we can work this in this field of work.
Which one?
Effect of irregularity on the propagation of different type of surface wave like love wave and torsional wave will be situated. The development of systematic seismogram for torsional surface wave is the key of objective of our future research. Problem related to Rayleigh and wave will be studied. In addition of other seismic wave type G type seismic wave will be analyzed in future as well.
Okay, you have developed 1 to 5 chapter. Which one is your favorite chapter? Which one is your favorite chapter?
Chapter first is favorite.
Why? Chapter first is introductory.
Chapter 2 is first is introduction part.
Which result is influence you more?
This is the chapter is favorite.
Why? Why this one?
So is we solving this? So all paper is favorite, but this is paper is also.
Okay. Dinesh?
Sir. Ayush?
Yes, sir.
So from my side, the all questionnaire is clear. If any question from audience side, they can ask.
Any question from audience side? Any question from audience side? Okay, there is no question then.
Okay, so what we observed during the Viva provided the clear and structured presentation and research and a problem, objective, methodology, and key findings also demonstrate a strong understanding and underline the mathematical theories and techniques and used on the basis. Responded confidently and competent and a question and a potential to uh, all the questionnaires significant and a corporate and non-homogeneous and a research in future work. The candidate shows the command on the subject and display the analytical majorities. The mathematical modeling and theoretical results are highlight the quality and contribute the original insights in the field of mathematical modeling. The thesis is well organized, well written, and a clear mathematical language. So, from my side, based on the candidate performance and the Vivagosi examination, the quality of the research work, what we observed, and eventually had recommended that Mr. Manish Kumar is known as Dr. Manish Kumar. So awarded as a PhD degree in mathematics.
Thank you, sir.
Thank you, sir.
Thank you, sir. Now I want to give thank to every respected teacher, especially head of the department mathematics, Dr. S.B. Rai sir, Professor P.K. Chaudhary sir, Principal Patna Science College, and all the respected teachers and my colleagues and research scholars. I would like to give many thanks to all of you. Thank you, sir. Thank you.
Thank you. Thank you. Thank you.
Natap ki.